Okay, solving a logarithmic equation. We've got, again, some mix of terms that have logarithms and over here a term that doesn't. When we do that, what we want to do is combine those logs. So we have a sum of logs here. We can combine them using our product rule. This can be a single log base 3 of x plus 4 times x minus 2. And then we take the next step to use the definition of logarithm to rewrite this equation in its exponential form. The definition of logarithm says we take this little 3 down here, that's our base. We raise it to the power, which is the answer from our logarithm, and we set that equal to the argument, which I'm going to go ahead and FOIL this out because we're going to need to do that anyway. So I have x squared minus 2x plus 4x minus 8. So 3 cubed, that would be 3 times 3 times 3, which is 27. And I do have some like terms here in the middle. That ends up being plus 2x and minus 8. This is now a quadratic equation. Anytime we have a squared variable in there, we have a quadratic equation, and we need to use one of our quadratic solving techniques to solve it. That would typically be either factoring or the quadratic formula. This one looks like it's going to factor pretty easily. So we need to look for factors of negative 35 that add up to 2. So I am specifically going to use a minus 5 and a plus 7 here. There's our factors. Set each one of those factors equal to 0. And we get 2 possible solutions. However, remember with a logarithm equation, we do need to check our answers. We need to make sure that the argument of the logarithm in our original equations is not negative. We can't take the log of a negative number. We can't take the log of 0. So when I put in x equals 5 up here, 5 plus 4 is 9. Oops, that's positive. That's good. And 5 minus 2 is 3. That's positive. That's good. So this is a good answer. Check with the next x value, negative 7. Negative 7 plus 4 is negative 3. So that means this is not a good solution. We can't take the log of negative 3, so we don't even need to check it in the other term. Next one up, number 17. We want to solve this for x. We have a nice little exponential equation here. So if we're going to solve for that variable that's in the exponent, the first thing we need for that part of the equation to be isolated. We need that part alone. So I'm going to divide both sides by 4. After I do that, I have 5 to the 2x equals 24 divided by 4 is 6. Now, to get that variable out of the exponent, the next thing we want to do is we want to take the log of both sides of our equation. So we have log of 5 to the 2x equals log of 6. Take log of both sides. You could use log, you could use natural log, as long as you have the same base on both sides. We do that because then we can use this property of logarithms that allows us to take this exponent and move it out to the front. So this is equivalent to 2 times x times log 5, and that equals log 6. On the left-hand side, we now have things multiplied together, 2 times x times log 5. So to solve for x, we need to divide both sides by the 2 and the log 5. The 2's cancel, the log 5 cancels, and we have solved for x. This is what we would call our exact solution. Okay, we leave it in symbolic form for our exact solution. To get an approximate solution, I think this one asks for both. That's when we would grab our calculator and go ahead and type that in. We have log of 6 on the top and 2 times log of 5 on the bottom. And we'll go ahead and round that to 2 decimal places, the approximate. Notice we want to round. Be careful with your rounding. Don't just stop. So x equals 0.56 when we round. This is the approximate answer. Okay, number 18, another exponential function. This one's a little different because this time we have an exponent or a variable on each side in each exponent, okay? So even though it's a little different, we are going to use that same kind of trick that we used before. We're going to take the log of both sides of this equation. So we have the log of 3 to the 2x equals log of 5 to the x plus 1. Again, you can use log or natural log, it doesn't matter. We do this because the property of exponents, one of our properties of exponents, one of our properties of logs allows us to take that exponent and move it out front. So then we have 2 times x times log 3 equals x plus 1 times log 5. Okay, we can't solve for x when it's stuck up in the exponent. It's floating in midair. We got to get it out of the exponent. And this is how we do it using logarithms. Now, this equation maybe looks a little complex because of the log, but what you need to remember is that log of 5, that's a number. Okay, you would know exactly what to do here if you had 5 times x plus 1, right? Our next step would be to distribute. Well, guess what? You don't have 5, you have log of 5, but that is still a number. So our next step is still going to be to distribute that logarithm because we want to clear any parentheses if we're trying to solve for x. So what we have after we distribute is x times log 5 plus 1 times log 5 is just log 5. Good. Now we're solving for x, so we need both the terms with x's to be on the same side. Again, you would know what to do here. If this was 5x, you would subtract it to move it to the left. Same thing with the logarithm. Log of 5 is just a number. It's some kind of decimal. I don't know it, but we could put it in our calculator. So I subtract x log 5 from both sides. So then I end up with 2x minus, 2x log 3 minus x log 5. On the left, on the right, these cancel because we subtracted them out. We just have log 5. Again, keep in mind solving for x, so we now want to factor that x out front, so we have it just in one place. We're solving for x, and we have x times something, so we need to divide both sides by that thing. So I'm going to divide both sides by 2 log 3 minus log 5. Over here on the left, they cancel, and we have solved for x. And then over here on the right, we have our answer. Now we are going to rearrange that just a little bit. So we have x equals log 5 over 2 log 3 minus log 5. And we can simplify that denominator a little bit through our properties of exponents. So first thing I'm going to do is I'm going to take this 2, and I'm going to kind of do the reverse of what I did at the beginning of this problem. I'm going to move that 2 into the exponent. So log 3 squared minus log 5, which 3 squared, that's 9, right? Okay, so 3 squared is 9. I'm just going to go ahead and simplify that. Look, there we go. There we go. And then what we can do, we have the difference of two logarithms, and those can be combined into a single logarithm through the quotient rule, through division. So that is equivalent to log of 9/5. We could even take it one step further if we want and use the change of base formula to write it as log base 9/5 of 5. But either one of these is a nice final answer. Again, the symbolic answer, the answer with the logarithms, that is your exact answer. This problem, does it ask for it? Oh, it only asks for an exact answer, so we're good. If it asked for an approximate answer, then we would take that result and put it into our calculator, and that would give us our approximation. Number 19, Hadil deposited $5,000 at 9% compounded continuously. Find the time required for the amount to double using continuous compounding. So continuous tells us which of our interest formulas to use. Continuous goes with the one with the natural exponential in it. And we are starting with $5,000, so that goes in place of P. Our interest rate is 9%. and it says find the time. So we're solving for t this time for the amount to double. So if we started with 5,000, it doubles when it reaches 10,000. That would be our ending amount. So there's our equation we need to solve. Going to divide both sides by 5,000. And 10,000 divided by 5,000 is 2. That's that doubling. It comes out nice and even. Again, when the variable is in the exponent, we are going to use logarithms to move it out. And I am going to use natural log this time because of the e. The natural log and the e are going to work well together. So when I take the natural log of both sides, I get the natural log of 2 equals. And then over here, this is where I grab that exponent and move it out front. That's the property of logarithms, one of them. Okay, the natural log of e. Let's think about what that looks like. The natural log is log base e of e, and that is asking us what exponent do I put on e to get e as an answer? Well, it's 1. When these two match, the answer to the logarithm is 1. So this whole thing is just equal to 1, and when we multiply by 1, that doesn't change the answer. So that really just goes away. We can mark it out. And now we just need to solve this little equation that's left over here. I'm going to divide both sides by 0.09. So t, the time for our money to double, is going to be the natural log of 2 divided by 0.09. It does ask us to round to 2 decimal places, so we'll put that in the calculator. Natural log of 2 divided by 0.09 is, we will double our money in, and it says 2 decimal places, 7.70 years. And number 20, a drug is eliminated from the body through urine. Suppose that for an initial dose of 75 milligrams, the amount A of T in the body, T hours later, is given by A of T equals, we got a nice little exponential function there. What is the half-life of the drug? Okay, when they are asking for half-life, they are asking us to solve for T. And specifically, the half-life is how much time does it take for us to have half the amount we started with. So here's the function. They gave us a nice equation here in this problem. We should recognize, but also they spelled it out in the problem, when you have an exponential function, the coefficient here on your exponential is your starting value, okay? And it also says up here, we had an initial dose of 75. So if we are asked to find the half-life, 75 divided by 2 is 37.5. So that's going to be our ending amount. When will if we start with 75 milligrams, when will we have 37.5 milligrams left? Solving for t. It's going to be really similar solve to the previous example. We're going to start by dividing both sides by 75. 37.5 divided by 7.5 is 0.5. Half-life, that's the 1/2 right there. And we need to take the log of both sides. You can do natural log or regular log. I'm going to do natural log this time just for fun. This is where we can then take that t and move it out front. That's one of our properties of logarithms. It's why we use the logarithm here. T times the natural log of 8.8. So we need to divide both sides by the natural log of 0.8. And there is our answer. T is natural log of 0.5 divided by natural log of 0.8, which is, we are going to grab our calculator. It does ask us to approximate to 2 decimal places. Natural log of 0.5. If you have the multi-view, you can use the fraction for that division. If you don't, you just use the division key, just divide those two. And our answer is 3.10628. It asks us to round to 2 decimal places, so we'd want to round that to 3.11. We have a word problem, so let's label it. Back here at the beginning, it tells us that we are measuring t in hours. So this is 3.11 hours is our half-life.